in Jena as for the best graduation project over 2 years. So I think it's extremely impressive that Achim can come back and concentrate on something like this now. So thank you very much. And the second talk is about Morpho-Ecologies.
Yeah. Because I have that pleasure of giving the second talk, I would try to actually quite link them, although there was a lunch break in between, to link these two together. So just quickly recapturing what I tried to outline in the first talk was that I was really trying to explain different ways of differentiating structure through digital morphogenetic processes which are enabled by evolutionary computation and artificial life. That was the idea. So we can understand genetic engines really as engines for differentiation. And I think that word has already come up as one of the drivers of somehow the underlying design strategies that we try to employ in the talk by Mike and George. So if the first talk was about enabling ways of differentiating, then the second talk is more about the focus on an alternative architectural design approach that is directly related to the potential that comes with these morphogenetic design strategies. Because I think somehow an approach that really tries to strategize differentiation becomes really interesting, because today we not only have the possibilities to generate somehow complex structures, but we also have possibilities to really understand their performances far beyond just as a load-bearing device. I think with the latest finite element analysis, computer fluid dynamics, or things like digital multiphysics, where you have the interaction between solids and fluids and things like this, you really have the possibility to investigate the integral behavior of complex structures and their capacity to modulate somehow performative conditions such as climatic, acoustic, and light conditions. And they are all resultant from the actual way you strategize the employment of structure. I think this becomes then especially interesting if we understand the built environment as an ecological, topological, and structural provision that facilitates human activities. Because then we also understand that the differentiation of these structures intrinsically modulates and differentiates exactly these conditions that enable the inhabitation of space. And I think this is interesting because it's very different to design approaches that try to match spatial units or locations with singular ways of inhabitation. And I think that's the way architecture is usually done, or was one of the paradigms of modernism, that we try to match a particular program with a particular sort of allocation of a spatial unit, something like a living room, sleeping room, and so on. So what I try to promote is really a shift from an approach that facilitates program requirements in specifically assigned units to one that provides a range of conditions that then enable differentiated ways of inhabiting that space and thereby ultimately provide a more adaptive and responsive built environment. So the core of a morpho-ecological approach is really to strategize the organizational effects of differentiated structures as the relation between differentiated morphologies and the emergent performative macro and micro environments. So if we aim really at enabling a performative and complex environment, I think it is somehow it really necessitates to think about structure more not as a static object, but as a condition that generates and differentiates far beyond just carrying the loads that need to be brought to the ground. So in my article, I try to present actually two ways or two morpho-ecological design strategies that outline ways of somehow coming up with a structure that could operate in such a way. The first strategy instrumentalizes more local manipulations within a global system. And I try to explain it in my AD article about through a competition project for a landscape playhouse. The second strategy that I outline is based more on the proliferation of a parametrically varied component into a larger differentiated system. So it's actually two opposed ways of going about it, but they both aim at the differentiation of structures in order to modulate differentiation of conditions that enable the inhabitation of these spaces. For that talk, I would like to focus on the second strategy that I outlined, which is the component proliferation. This has two reasons, actually. One is that it's simply too short time to show both strategies. And second, because I got that award yesterday, I have that already prepared, so I can show you that part. So this strategy was actually explored through a project that I did that was called Post-Agriculture. And in order to really understand the way you can make such a morpho-ecological strategy operative for yourself, I have to give a small introduction, really short, into the aim and context of the project. The aim was really to rethink agriculture production in the Netherlands because of a very special situation, which is that on the one hand, the Netherlands are the most densely populated country in Europe, and on the other hand, they have the highest agricultural land area, productivity per land area. So you have to imagine that actually means ultimately an enormous pressure on the Dutch landscape, because 1 square kilometer has to actually house more people than anywhere else in Europe, and at the same time you have to grow more agricultural products on that square kilometer than anywhere else in Europe. So there's quite a conflicting pressure. The response of the Dutch government to this extreme situation is just to stack up agriculture production in one huge building. And why I'm showing that is that because I think this is the classic of the more unit or program-based approach that I try to somehow question a bit with the morpho-ecological approach. So what you really do is you take one program, for example, livestock, and you just give it one particular space, and then you stack different spaces on top of each other. I mean, obviously, these layouts or a unit-based design is really highly static and quite exclusive. So you can imagine that once the demand for agriculture products changes and things like that, it is quite hard for an organization structure like that to respond. So what I tried to come up with is that alternative condition-based design, which actually releases the pressure from the landscape through alternative agriculture production that is hybridized with recreation activities, because that's actually the demand on land use by a high density of population. And that is enabled by a deep and differentiated structure that doesn't provide somehow spatial locations that are related directly to one program, but it actually provides differentiated conditions that then relate to different activities. And because these conditions are changing or capable of changing, and only some of them are somehow hard controlled, you enable the mutation and migration of activities, and thereby you really create a responsive environment. So obviously the first question was, how can one combine seemingly opposed and quite complex recreational and agricultural systems? And in that image, I tried to map out the recreational and agricultural systems that need to be incorporated and the related sub-processes. So this is really an activity-based chart. And then the project really employs, and I think that's something that needs to be considered for any morpho-ecological approach, is somehow a dynamic organizational model of the intersystemic relations that you try to strategize. So the way that model works is actually that it traces dynamically the light and temperature requirements of each system and sub-process, which is just simply laid out on a grid over time and intensity. So you can see different intensities of light and different intensities of climatic actually temperature that are required for recreational and agricultural processes, because these are the main criteria that you need in order to enable horticultural activities, for example. Because nowadays, and I think that's also important to say, they are quite independent from somehow the spatial articulation, because they just float in the air, more or less hang and the roots are, it's called an aeroponic system. The roots are sort of just in mid-air, and you inject substrates directly to the roots. So you don't need a surface to put them on and things like that. It's really what is enabling agriculture production is the conditions. So that organization model then can actually map the intersystemic relations and really indicates potentially shared conditions of various degrees for different systems, and this is somehow part of the model that strategizes the light relations, and these are the temperature relations. The question here obviously is what kind of structured system could then provide for such a highly articulated and differentiated microenvironmental layout that is promoted by such an organization model. So what I tried to do is or what I started off with is an investigation into pneumatic structures, because I thought that their nonlinear and quite complex material and structural behaviors suggested a high potential for differentiation. So the aim of what you're going to see now is somehow to unfold the organizational capacity of such a material system to organize and modulate dynamic microenvironmental conditions. The development of that started with an evolutionary process towards a highly specific pneumatic component that started off with a very simple pneumatic cushion that was then continuously informed by digital form finding, which you see on the right-hand side, physical form finding on the left-hand side, and a subsequent digital analysis on the lower right-hand side. So the base, as I said, was a simple inflated cushion, and that was then further, so here you see the cushion, which was further differentiated through 4 parallel seams, 7 parallel seams, then the introduction of 6 crossing seams, 8 crossing seams, 12 crossing seams, and then the evolution of first optimized component with further geometric differentiations and the resulting more specific component, which is based on a relatively simple geometric principle. And I think that is what George already outlined, is that you actually create, through an additional seam in that case, a shorter and a longer surface, and thereby, during the inflation process, the membrane gets pre-stressed and it's actually forced into a 3-dimensional shape. So that's what you can see in that sequence. Depending on actually the sag that you allow at that seam and the pressure of the inflation, you can strategize somehow the change in geometry. This can obviously then be further exploited by multiplying the component into a local multi-chamber system. And this is where there was the first, or I hit on the first problem, which is actually that any form-finding software for membranes that you can now employ actually operates only with static definition points. So as this multi-chamber component is obviously dynamic, when all the boundary points start to shift, I had to introduce somehow a combination of an animation and a membrane form-finding process. So first the parametric setup was done in an engineering software, and then exported to an animation program, which allowed to animate the definition of the boundary points, which then again allowed for a dynamic form-finding process of that membrane. And that ultimately enabled to actually generate a digital membrane model of that prototype, or of that multi-chamber component. That multi-chamber component has different inherent articulations of the membrane model, with the possibilities for further parametric relations and parametric variations that are still all coherent with the initial component that you start off with. And the structural principle of that self-supporting multi-chamber component is actually relatively simple. It's just 2 mutually stabilizing forces. One is the internal pressure that pre-stresses the membranes and forces the components into a 3-dimensional articulation because of the shorter lower seams, so the whole thing lifts actually itself up. And then you have the resulting tension in the seams that stabilize the system by just being pulled down to the ground. So you have two systems that work against each other and thereby stabilize themselves. Because that is all digitally derived, it's actually a relatively simple step to derive a cutting pattern in the same software that then allows the rapid manufacturing of a physical prototype of that multi-chamber component that you can see here in the process of inflation. And this prototype is really a self-supporting pneumatic structure in which the seams become also structural elements. And I think what is interesting about the process so far is that it is really based on a feedback between the physical and the digital modeling that allows to exploit the capacity of the material system and at the same time investigate and inform the process by the parametric variations of the system itself. So there was a whole set of other parametric differentiations that are possible and that were identified through digital definitions and tests, always in relation to the modifications that you do to the system on the top and the differentiated light patterns which are actually registering the energy that is transferred through the cushion at a registering surface. So it's really about ways of differentiating that light and energy transmission. So the first possibility is varying the translucency of the surface material, obviously. Then you can actually vary the depth of the pneumatic chambers. You can work with a change in density of the seams that creates different patterns of illumination. And obviously you can also have differential reinforcement of the structural seams. So having investigated these possibilities of somehow in an integral way modifying the structural possibilities of the system and at the same time the possibilities of the system to modulate interior conditions, it becomes obvious that there is also a need to actually support that system by itself. So that's what you would conventionally call, I guess, a primary structure. But here the idea was really not to articulate a primary structure as a discrete element that is merely supporting the actually differentiated pneumatic system, but the idea was to articulate the supporting structure as a continuation of the structural seams, so that you actually create one continuous system of seams in which just the material articulation of the seam changes along its path, from just a welded membrane to all the way to an aluminium rod, all the way to a concrete anchor. So in that slide you see 6 variations of the interrelation between the pneumatic cushions and the reinforced seams. And these parametric variations allow then to proliferate the component into a much larger system. And I think what is interesting to see in that animation is actually that although the system starts to become differentiated in a generic way, you can see that each element is still coherent with the logic of the initial component and the logic of the multi-chamber component. So what you end up with is an open system that can extend into a much larger structural system. So what you see in the next animation is somehow the way that can proliferate further and extend not just horizontally, but also vertically. So what you end up with is a multi-layered system that consists of a lower layer with relatively short spans, a mid layer of more pneumatic surfaces, and a pneumatic top layer. Now what is obviously interesting is to see how that system that carries the possibility for differentiation can respond to really the site-specific layout of macro-environmental hard-controlled conditions that you need to somehow facilitate. Therefore, the system was exposed to the particular climatic and urbanistic context on the site. So what you can see here is somehow the site-specific distribution of the macro-environments that you actually need in order to facilitate a certain amount of agriculture production and leisure activities described actually as an interrelation between temperature conditions and light conditions, nothing else. And somehow you also have to provide for the macrosystemic connectivity and a couple of ecological links. So in the next animation, you see the adaptation of that developed system, to the very site-specific requirements, starting from the very basic layout that we have seen beforehand, and then the adaptation to these macrosystemic requirements that are enabled by the parametric variations that I explained earlier. So here you see the site-specific or overall structural articulation and the way it is embedded into the particular context on the site at the seafront in Holland. So that is the articulation of the multi-layered differentiated post-agriculture landscape that is now fully differentiated. So it's actually the next step after the generic system that was informed by the macrosystemic layout. And now it's interesting to see how, by all that external information, the system is capable of creating microenvironments that are then enabling these programmatic mutations and migrations that I talked about. So I will try to explain that by just showing you a more detailed section of the model, which is just a cutout at the bottom end, which I will start from the top. So here you see the top surface with a permeable parameter that enables the recreational agricultural circulations, because that is somehow seamlessly embedded into the surroundings. Then if you go down for one level, you see the upper mid-pneumatic surfaces and the lower mid-pneumatic surfaces that are actually held up or supported by the primary structure that evolves from the differential reinforcement of the seams, and these become then at the same time the service infrastructure. I think that's what you can see in that slide quite nicely. And then if you go one level further down, you can see how the infrastructure becomes more capillary, thereby the spans become smaller, the cushions become thicker, and the seams denser. Below that there is another layer of pneumatic surfaces, and at the very bottom there are actually a couple of water basins that can be used for fish farming and are mainly required as the thermal mass. And that brings us to the way you can actually investigate now how that very specific system creates very specific microenvironmental conditions. So in order to do that, I set up a simulation model that enabled a temperature analysis that incorporated the internal and the external energy sources, and a light analysis that was run over 1 year. These are actually just graphics, because the two analysis models look exactly the same, because they use the same way of color coding information on the range from blue to red, actually. So I think this then indicates how the structure, by responding to the different load-bearing requirements of the different systems that need to be accommodated, can provide really differentiated macroclimatic zones. So in that slide, you can see actually, for one cutout of that model, the microclimates that correspond with the initial organizational model. So you have to imagine, first you start off with macroclimates, which are much larger zones, and this is somehow the evolving differentiation of these larger zones that are derived just by the manipulations of the system. I think what is more important to see in that image is that the analysis also indicates somehow the gradient transition from these relatively hard modulated zones to a negotiable field of soft modulated areas that then really enable the program migrations and mutations in these buffer zones that would enable a more responsive way of actually accommodating a production landscape. So I will just quickly explain on a relatively polemic example how that may really work. So for example, if you look at one particular area that is highlighted with that orange circle, and this is a relatively stable, hot and bright area, you can see how the organizational model suggests for that particular condition that is found in that area, manifold of programmatic mutations. So you get all kind of different links with different intensities to other systems that actually this activity could transform to. And this means that the example area could, and you see an interior view here of exactly that area, that could cater by its initial definition for example, plant propagation processes. Then it could transform into an area of horticulture production that is interwoven with recreational activities, as for example, that's what I call an oxygen beach. And it may also cater for more short-term events, like a greenhouse rave, by just temporarily increasing the pressure in the pneumatic structure. Furthermore, coming back to the initial sort of section model that was investigated, the structure obviously organizes the systemic connectivity and the service infrastructure, which is extremely important for simultaneous cyclic agriculture production processes. So there's actually, just by nature of the way these things are done, there is a migration of programs. And then at the end of the day, you create quite highly ecological links that are intrinsically related to the layout of the structure. And just to communicate that, this was all developed in relation with the Dutch Ministry of Agriculture and a couple of agriculture research institutes. So there was always also another sort of meta external information of how these things may really work out and what needs to be informed and how the structure becomes truly operative and performative. So if you look at the final image with the structure layout, the related topological relations of the different surfaces and thereby the connectivity that is enabled, and then the related microclimatic zones, you can really see how the project tries to promote an integral approach of geometric, topological, structural, and environmental aspects. And I think this can then yield an intense morpho-ecological relation through the very careful calibration of the manipulations of the actual system, the dynamics of the environment, and the respective modulation of the performance of the system. So if I would summarize that, I would say in a morpho-ecological approach, somehow the architectural design is really thought of as an ecosystem that organizes the use of space in an inclusive and time-based performance package manner, and that allows then for a denser and more responsive environment. Thank you.
Thank you, Achim. And of course, the quality of the rave could depend on the sort of mushrooms you're growing there as well. But now, if everyone would like to take a seat who hasn't got a seat, there are a few at the back here, or possibly if you move towards the windows, some seats. Is anyone standing who would rather be sitting? It's probably more comfortable for everyone to sit if they can. And so on to the second presentation of the afternoon by Michael Hensel, who again is one of the co-directors of the Emergent Technologies program here, and also a partner at Ocean Law Architects. So, Michael.
Okay. For those of you that know me, it's probably quite telling that Achim is coming over to help me set up the PowerPoint presentation, which gives you an idea that the tone and the focus of the presentation will change with respect to what has been presented so far and what will be presented after. I would like to start this whole presentation with a personal note. I feel kind of blessed to have the opportunity to work with colleagues who can match their curiosity with knowledge, because I cannot. I don't know exactly what I'm talking about. Nor do I really have a point to make, nor do I know the technology that is at the heart of the work that I'm showing. But what I'd like to do, and I'm perfectly honest about it, what I'd like to do is initially to eradicate the anxiety that might exist, or maybe it's just self-therapeutical for myself to talk myself out of it. Two types of anxieties. Number one, what happens to the designer in these kind of processes? And I'm nothing but that. I'm somebody who operates on curiosity without knowledge. So be assured, it's no problem. Second, I would probably break my finger in the attempt to switch on the computer. That should address the anxiety of what about all this digital technology. I think the point that I would like to make is, being somebody who comes out of the rotary generation without having made the leap to operating the next tool, you don't have to. I think a lot of the work that you're seeing today is based on collaboration, and necessarily so because it's spanning disciplines and eradicating disciplinary boundaries. So what I will show has by no means ever been produced by myself. I probably just try to give some input in terms of curiosity and lateral thinking, trying to figure out how one thing connects to another, and I think who should really be credited with all that work are my colleagues from Ocean North, and most notably Achim, Mike, of course, and also Jeff Turco, he's sitting here in the audience, who has collaborated quite often. And also I would like to really extend my acknowledgement and thanks to the students of the MTech and DIP4 programs who permanently help when I'm once again incapable to even get the PowerPoint presentation going. Having said that, my task for today, okay, so something is wrong here, Achim. I just pressed there, but this won't help you. Ah, that's not my fault, no?
I have to be diplomatic now.
Yes. Thank you. Yeah, that's what I was doing. Okay. What I would like to do in trying to weave an argument in and out related to two of the essays in the forthcoming AD issue, I would like to pick up on the notion that was introduced by Mike and discussed by everybody else since. What are the consequences of considering material form as dynamic, which is a problem that has been recognized in the past by many. And the two essays, respectively Finding Exotic Form and Fit Fabric, raise two issues with respect to dynamic form, or the dynamics of material form. Number one would be, how does one derive material form from the dynamic interrelation between intrinsic characteristics of materials and material systems and influences from the environment? That's a process that is called, so far, form finding, and it's usually done through physical experiments and modeling. But also there's a great wealth of digital tools for that as well. And second, how does material form evolve in relation to its interaction with the environment once it's constructed? Because form finding essentially has two tasks. Number one is to find the form to be constructed. Number two is to devise a chronological relation in the construction process to get the form constructed on site. And then what happens with it? More specifically, I would like to relate three questions to that. How can formal articulation be derived from a multi-parametric form-finding process that relates geometric, material, spatial, and programmatic requirements and logics? And the problem here is that form-finding is usually done on the level of a structural interest. How will a form stand up? So how can one bring in more requirements into that mode of thinking and evolving form. Second, what would then be the status of efficiency and redundancy in such a multi-parametric process? Obviously, to deal with one parameter only means that you try to make your form that you evolve or your structure that you evolve with the minimum effort in terms of energy and material to perform that task. But if it has to perform multiple tasks, and if these even seem to be contradictory, how do you cope with that? And thirdly, how can dynamic interaction between material system and environment be strategized in the design process? But I think I will just somehow scrape along that subject because I think Achim has discussed that in great depth. So here's a definition for form finding. Basically, what one sees here is a definition between the tendency of any kind of material to organize itself into a structure or other kind of performative shape in reaction to forces and influences from the environment in which this material is placed. So a typical experiment of such kind, and one of the early ones would be Antonio Gaudi's hanging models for the Colonia Güell church. But what is really interesting, and what is oftentimes just simply not said, although everybody knows it, form finding in almost 99% of all the cases leads to curved geometries. There are some cases where that is not true. If you think about the minimal path experiments that lead to tree-like structures, but if we really want to discuss tree-like structures, we better refer to George's presentation from earlier on, and then we see that we're back to curved geometries and not to straight lines with angular connections. So among those form-finding processes that lead to curved geometries, we have obviously the minimal surfaces, soap bubbles without any controlling edges, external controlled edges for soap film experiments. Obviously, we have the tensile stress suspended form, with linear elements, catenaries, and with flat elements, the suspended nets. We have, of course, the compression stressed inverted forms with flat elements like the grid shells, or with other flat elements such as the thrust surfaces as more continuous elements. And of course, this applies also for natural structures, whether in living or non-living nature. You have on the one hand the tensile stressed, for example, for membrane forming materials and compression stressed material conglomerations, rubble heaps, drain funnels, caves, erosion formations, and also structures that Frei Otto called structures in space and time, such as waves, systems subjected to vibration, vortexes, and turbulences. So all of that somehow, strangely, has an underlying relation to curved surface geometry and to curvature. I think here it's probably worthwhile, even for somebody like me who knows nothing about computation, to say, hold on, why are we seeing all these vegetable shaped buildings that are coming up these days? Is this merely a formal preference of the time, or what does it actually imply? Presumably we will hear for the rest of the afternoon, and probably we have already heard, that it implies a lot. It implies a reaction to an external environment. It probably implies a relation to how a material will shape itself under certain given forces. Now a curve is just simply said a geometric object that is one-dimensional and continuous. I guess in topology it's called a path. And curvature is the amount by which a curved surface or other manifold deviates from a straight line or plane. And there are two ways in which curves can generally be described. One is by its parametrization, which is really interesting because it means it's easy to compute. And the other by determining how much a curve bends at each point. The measure of bending is then called curvature. And curved surfaces obviously yield a great potential for architectural design. This potential must be understood as coordinated and interrelated geometrical topological one with significant repercussions on the design, manufacturing, assembly, behavior, and effect of the material form. The design problem is how can geometric, material, and structural logics be coherently developed in order to arrive at a complex curved surface with high performative capacity. But I do think that Achim has gone into that, and he has also made a relation to how even the manufacturing, construction, or assembly process might be integrated in that. And I'm sure we will hear more later on from Charles and from Johann Sischka about that topic. Now, what I would like to do is run you through a series of design ideas that are related to that, and some low-level computational analysis and techniques that first and foremost bring about somehow a conversation of geometry, or rather, how does one derive form, what kind of geometric definition seems adequate in order to satisfy various performance criteria. And this will also involve, just to address one of the earlier anxieties, just merely design criteria. On the level of something not being performative, but being potentially even to the point iconic for a certain body of work. So I have no qualms with that. These kind of criteria can also come in and inform a design. Okay, and the first project that I will briefly discuss is Ocean North study for World Center for Human Concerns for New York, which was designed for an exhibition at the Max Protage Gallery. This project tackles the topic of curved geometry as a performative envelope that delivers space around an existing volume, or rather no longer existing volume. We assumed that the World Trade Center towers, the Twin Towers, are still there, and we would wrap a new building around these volumes. Some identification of the problem of densification in cities like New York. The initial form finding criteria for the World Center were concerned with the experience of an unfamiliar form. So here we have a third element coming in, not just form and environment, but also the inhabitant. How do you actually experience something like that, and how may questions of form finding be extended to that realm as well? So it was concerned with the experience of an unfamiliar form with respect both to its global geometry and the local sectional articulation of the scheme as a series of interstitial spaces formed by a skin draped around the volume. The form is 440 meters tall, and it evokes a sensuous image of continuity and multiplicity. It's very difficult to tell initially whether one looks at one or several forms, which is a question towards the geometry, a question towards the seam. The seam is a question of manufacturing, construction, structural performance, etc. So appearance and all these other criteria relate quite strongly. The project is not concerned with the representation of emergence as a formal feature, but rather with the potential of unfamiliar form and the spatial organization to yield experiences that may lead to emergent social arrangements. And that is for an institution that doesn't exist, whose constitution is to be written, for a World Center for Human Concerns, so an architecture that yields an idea for a potential institution. This was done with an off-the-shelf piece of software to inform what you may want to loosely term a form generating process. So it has nothing to do with the sophistication of the processes described earlier on by Achim. It is just a very simple software that drapes a surface around an existing volume. This is quite easily done with readily available software. And each frame of such an animation is a snapshot of a kind of formative process. However, it can also be understood as a potential configuration. So you can derive geometries from that and analyze those geometries. So this envelope was draped around the volume of the Twin Towers, which you can probably vaguely guess from the bottom of these kind of footprints. It's shining through here. But as a building that is draped around it, the design problem is to resolve the required structural independence of the draped building from the host building, which was not designed to receive additional loads, or even the building also has to deal with the increased internal circulation that the host building would also not be able to do. So in that moment in time, we considered that we could probably resolve all those problems by the skin of the new building. So one has to look at that envelope quite carefully, because that envelope receives quite a series of performance requirements. Number one, you can see that you get two intersecting volumes here, each of which needs to be analyzed in its form, but where also the seams need to be considered in terms of formal preference, in relation to the design attitude of that project, but also as possible structure, manufacturing, and assembly consequences. So the first thing that one would probably do along the lines of low-level analysis to make sure that you are somewhere on the track with coordinated performance of such an envelope is the geometric analysis on the curvature. What I first introduce here is Gaussian curvature analysis. Carl Friedrich Gauss had a major interest in differential geometry and wrote a paper that was called Discourse on Curved Surfaces, which was published in 1827. And it is valued as one of the most important discoveries in mathematics, which contains such geometrical ideas as Gaussian curvature. The latter measures precisely how curved a surface is at each point. Gaussian curvature of a surface at the point is a product of the principal curvatures at that point. But that is not so important. What's more important is, and I will go through the explanation of the repercussions of changes, what are different kinds of Gaussian curvatures and what are their repercussions in a second. But Gauss's work on curvature enabled eventually the leap from curvature of one-dimensional curves to two-dimensional curves in three-dimensional space. And that becomes the basis for even more sophisticated body of work on curvatures of three-dimensional surfaces in four-dimensional space. So positive Gaussian curvature or synclastic curvature is bowl-shaped, like in the upper example, and in the following slides color-coded as red. Negative Gaussian curvature or anticlastic curvature is saddle-shaped, like the lower image, and in the following images color-coded as blue. So here you have the two volumes analyzed regarding Gaussian curvature respectively. And what is important here is that Gaussian curvature analysis serves, among other purposes, to determine whether a surface is developable or not. What that basically means is whether it can be unrolled and produced from a flat plane or not. In a sense, once you do such an analysis, you can go two ways. You can either try to put a preference on a manufacturing process, and you could say, okay, we need to get rid of certain types of curvatures in order to produce everything from flat sheet. Or you could say maybe there's a differentiation in the manufacturing process simply by knowing that there are some areas which can be made from flat sheets and others that cannot. So it's a low-level analysis that allows you to assess these kind of things and make them design criteria for a further approach. Another low-level analysis is the so-called zebra analysis in software like Rhino, which uses NURB surface evaluation and rendering techniques to aid visual analysis of surface smoothness, curvature, and continuity between surfaces. Such an analysis of surface continuity helps to assess the structural consequences of how surfaces may meet or curve. Zebra analysis plots zebra stripes over a model as if it were chromium plated and placed inside a striped cylinder. This is actually a technique that is often used in the car industry to search surfaces for bumps, folds, and other deformations, which of course can or cannot be structural features if they are strategized as such. Zebra analysis can highlight the type of surface continuity that might exist within such a surface, and I'm not going through detail here, but these surface continuities may have repercussions on how you wish to consider where seams in a structure might lie and how loads travel across curves with different curvature continuity. One problem with zebra surface analysis as a low-level type analysis is, of course, that once you change the angle of view, the stripe pattern changes, and so it becomes very difficult to analyze and discern what exactly is the pattern that needs to be considered and possibly fixed or strategized. The zebra analysis of the World Center reveals all three types of surface continuities. That means either that one would remodel the building in order to somehow reduce the number of changes in curvature continuity, or one could make that a structural feature towards material approach in manufacturing. Now, another relatively low level, even though costly way of analyzing what you have and having also a physical output is, of course, computer-aided manufacturing, in this case rapid prototyping, whereby you can produce the physical form that you may have in front of you. This is quite often done in industrial design, and a lot of these technologies now venture into the realm of architectural design. This is quite often used to optimize the bodies for cars or motorbikes by moving back and forth between physical outputs, you computer-aided manufacturing, remodeling it physically and putting it back into the computer, analyzing it there and remodeling it digitally. So it's a kind of continuous process. Okay, so we're back to the form finding criteria for the World Center, which were initially volumetric with respect to the overall geometry of the building and with respect to the spaces that one derives through the intersection of these surfaces. So what you could imagine here, that one could begin to think of these spatial pockets as somehow the vertical equivalent of urban blocks that could be handed over to other designers. But if that would be the case, there has to be some sort of coherence in the structural system, or at least in the kind of rules that underlie the different designs that accumulate to this kind of volume. Then, if you want the skin to perform in various ways, particularly structurally and circulatory, of course you have to seek for the channels by which load travels and by which people travel. So the envelope is organized as two large interlocking basket structures, of which you see only the primary system here, that enable to absorb a much higher degree of local structural disruption. Imagine a basket where you take some strands out, you can still carry load with it. It's very different from having a singular structural core that gets disrupted. The greater potential of the envelope to flex and to distribute forces across the strands of the basket is given by the redundancy of structural members in a basket-type morphology. You have more than you need. The scheme also abandons the central service core and circulation core. Instead, through these structural elements, the circulation is solved by them being hollow. So you have 120 vertical circulation channels nested within the surface of this building, and you can probably calculate that it will take you a lifetime to explore every single possible way to your workplace, which I think delivers a third diagram to the two diagrams outlined by Robin Evans, the interconnected matrix of rooms or the corridor model. This is somehow the hyper-intensified corridor model, which becomes somehow also an experiential model. So we're back also making the link to the inhabitant. Okay, here you can see how these 120 channels would be nested within the facade. Important is then too how the facade is geometrically locally articulated and textured in order to regulate the transparency of that envelope. But Achim has gone into that topic quite extensively, so I will just mention it here. And finally, there's a question that arises once you approach such a building like that. Once you thicken the space around an existing building, you end up with incredibly deep floor plates, so how do you handle that? And here I think it's quite interesting to see that in relation to the question of daylight. Do you provide a homogeneous environment? Do you try to get as much daylight in as possible? Or do you actually take the somewhat more anarchical opposite view where you say maybe it's quite good to have a very dark core because a lot of people seem to be getting up during certain times of the day that are not the daytime hours and they're most active then. So 24 hours programming might have a totally different repercussion. It means providing an internal environment where dark zones, brighter zones, etc. are permanently simultaneously present rather than equaling out the environment. Okay, I think in that sense, in the way in which this kind of project tries to bring spatial, material, and ambient articulations forward to yield emergent social, representational, and habitational arrangements, it relates to Achim's argument early on of the morpho-ecological environment, but by introducing the experiential part more. I guess the next project deals with a slightly different issue, but is motivated by equal or rather very similar kind of tendencies. But in this kind of essay, the question was not so much regarding the form finding, but regarding the performance of a material system in a given environment. And here, basically, it was the development of a helical structural system through a process that was described by Achim earlier on. So I will also just scrape along this. It has been very much evolved like some of the morphogenetic experiments earlier on. So you can see that the form becomes differentiated through the kind of generative process that underlies the form generation. And in doing so, we also explored the possibility of having a redundant amount of structure in order to liberate the interior from additional structure and to be able to then articulate the spaces within differently. So I think what one wants to say here is that the higher level of structural organization emerges where through local differentiation in which microstructures intersect, wrap around one another, bundle and unbundle, come together, combine load paths and spread them out again. What that delivers is a great deal of flexibility in terms of hanging floor plates in such a structure, because the only thing you need is a sufficient amount of intersection between the helixes in order to span a floor plate across. So in a sense, resolving somehow the envelope as a structural entity gives you a lot of freedom in terms of the arrangement of the interior. Secondly, we were then interested, if we have a structural system, how do we go about the envelope of the building? The first analysis started by looking at surface tessellation of a fruit, in this particular case a custard apple, which was quite interesting in terms of the similarity of the different areas which are tessellated, and yet also the degree of variation of those across the surface. And we were searching what might actually be the purpose for that kind of articulation. But we soon realized we're looking at the continuous surface, and what seemed more appropriate, since we already had approached the component approach, was to refer to the shark skin, where you can imagine that interrelated and size varied panels might actually give the possibility for local interaction with the environment. So basically what we did is develop a particular panel geometry that, through its material articulation of anisotropic materials, that was actually an idea suggested by George, which are rotated 90 degrees, are able to flip with a minimum amount of energy from concave to convex. So you see such a surface panel. Obviously that would allow an opening and closing of the surface, this twofold surface panel in two directions, and to enable thermal flow, light penetration, etc. in a differentiated manner. Then the next task was to write a simple algorithm that would vary and map these kind of panels onto the helical geometry of the structure. This is just one surface patch where this has been done. And to speculate further, what would happen if these panels could open and close differentially. And that is quite interesting, because decentralized control is the general feature of self-organizing systems. It involves a decentralized architecture of information flow between components, decentralized control mechanisms in which each individual gathers information on its own and decides for itself what to do. So basically you don't have a central computational brain that controls all the different surface panels, but each of them open and close either in relation to the inhabitant of the space right behind, or otherwise in direct response with the environment. Even if some panels break, the rest of the building will still be able to be served. The self-learning capacity of the simple paneling panel processing units also happens locally. Each panel is independent, responsive, capable of modulating the passage of light, heat, and air through in both directions, and managing its own energy economy. The self-learning capacity of this panel is thereby local. and so is the control of it. The integration of structure and the responsive envelope offer an extended performative capacity. Increasing levels of differentiation of the helixes yield the potential for changes in the spatial organization, meaning now interior spatial organization. And the ability to freely place the floor plates, and then on the other hand to be able to control these kind of internal spatial divisions and partitionings also locally through the surface paneling. The responsive building envelope makes it possible to differentiate interior microclimates, both in response to the diverse needs of the inhabitants and to the overall energy balance of the building. The integrated strategy yields a versatile and adaptable fabric. So with that, I would like to finish the presentation. The thing is, I do not mean to propose any conclusion. I just meant to highlight to you two areas of inquiry that relate to the question, what happens if you do consider material form as essentially dynamic? So you have, on the one hand, the whole process up to the design, then later on to the construction, and then the presence of the building or the material system on site and its interaction with that. And I think we're at the point where we can become more precise with the questions, but we're probably still far from somehow more integrated, synergetic buildings that can already somehow showcase such kind of performances. I mean, in a sense, the multi-parametric is interesting, and we're moving towards that. We have buildings that can do a lot of things already quite responsively. But obviously for us that is never enough because we're quite ambitious, and so it's quite interesting to see where the next generation of these buildings will go. Will the logic of working bring about an independent architectural sophisticated level, or will we draw even more from non-living and living nature? And I would guess it's probably a conversation between these two options. Thank you.
Thank you, Michael, for a very helpful introduction to the implications in at least two different ways of thinking about how we can use emerging technologies in the design of buildings. And while we handle a little bit of technological change ourselves, I'm going to say a few words about our next speaker.